In this video, we're going to revisit the vector equation for a line and apply that to a position of a particle at a time t. So remember, we said the vector equation of a line, we have r of t vector equals r naught vector plus t times the v vector. So I've brought in a picture that is a little nicer for us to look at, right? We're going to consider this vector form of a line in space, and we're going to think about it as the path of a particle starting at that initial position and moving in the direction following the same direction as the vector v is specifying. So we can take this equation, just written nice with our bold vector letters, and r of t is equal to initial time plus some parameter time t, and then the v vector, breaking that down into speed times direction. So the vector v has a magnitude and a direction, which is the unit vector. And we can see this is a balanced equation because we've got the magnitude of v divided by the magnitude of v. Those cancel to 1. So we're kind of expanding this to change our thought process. So what I'm saying is that this position of a particle at some time t is going to be equal to its initial position plus its distance moved. And the distance moved in the direction of that v vector. So distance times speed gives us distance, a magnitude. Let's look at an example of a helicopter. So for this example, we have a helicopter. The helicopter is to fly directly from the helipad at the origin in the direction of the given point, which is 1, 1, 1. And we have a speed of 60 feet per second. What is the position of the helicopter after 10 seconds? So, this problem's set up to help us because we're starting at the origin and we're going to point 1, 1, 1. So we're dealing with a nice even point. And we could think about that v vector as being 1, 1, 1. So the unit vector is going to be equal to that 1, 1, 1 divided by the magnitude of the v vector, which is 1, 1, 1. So the magnitude of 1, 1, 1 is the sum of the squares square rooted, so that's going to be root 3. So my unit vector which in this situation I'll refer to as u, is 1 over root 3I plus 1 over root 3j plus 1 over root 3k. This unit vector gives the direction, the flight direction of this helicopter. So let's take the equation that we wrote prior, and we said that r of t, being a vector, equals r naught, a vector, plus t times some speed. Speed would just be a scalar. T is a scalar. Speed is a scalar times that unit vector, u. And this is going to give the position of the helicopter at any time t. Since we're starting at the origin, we say that r of t equals r naught. Well, r naught, starting at the origin, is my 0 vector, plus t, my speed is given, it is 60, and then times my unit vector, we just found that is 1 over root 3I, 1 over root 3j, plus 1 over root 3k. So as we look at simplifying this, we don't need that 0 vector in here. And the position of the helicopter at time t. I'm going to factor out 1 over root 3 since that's common to all of these. And so I have 60 divided by root 3, and 60 divided by root 3 simplifies to 20 root 3, 60 over root 3 if I rationalize that. That's what I did to get the 20 root 3. And so my video skipped, but I don't need that there. So I've got 20 root 3, I still have my t in front, times I plus j plus k. So this gives me the position at time t. And if we want to find the position after the helicopter is in the air for 10 seconds, that would be 20 root 3 times 10 times I plus j plus k, or rather 200 root 3 I plus j plus k, which is the same as writing 200 root 3. I'm going to put my vector notation in there. 200 and root 3, 200 root 3, 200 root 3. So this represents a point in space after 10 seconds. It has traveled a distance of 60 feet per second for 10 seconds, which equals 600 feet. If we were to find the magnitude of this vector, we would end up with 600 feet. So that's the length of the vector from the origin to the endpoint. So that's the length of the vector r of 10.